Okay, let me start recording. Okay, again, good morning, everybody. So, Christina. Yeah, so if it shows that there's a graphing part in the free response, then yes, it's most likely a volume or a centroid problem. Okay, I'm just not sure which specific question that would be, but typically it's a volume problem because that's, I guess, the most I guess it would be easier to ask you to set up the integral for a volume in the free response part than the multiple choice part, so you can get partial credits if you get part of the setup correctly. But another option would be centroids, because that will test if you can compute the areas properly, and also if you can remember the formula for the average x and y value. So yeah. But if I am to bet, it would be a volume problem. Okay, yeah, okay, that's good, Fatuma. I also got a request from Brian, I guess, to answer some review problems. Um, I have here the practice test that Professor Almus posted in CASA. But if I understand it right, you also have sort of a different practice test in CASA, an online version of it. So if you have, though I don't have a copy of that, so if you have specific questions from that test review, then kindly send them to me. But here, while waiting for your questions, which you don't usually send them, so I'll just look at this review sheet and then look at some problems. Do you still have some difficulties with the U substitution part? Or have you already are you already used to it? Because here for okay, good. So probably I can skip that because we only have 50 minutes today. So yeah, let's see. I have here an interesting question. Let me see that. Okay, which I labeled as an extra problem. Okay, let me just enlarge this so you can see. You know, I'm not sure if you can see the problem clearly, but here we are given some info about the area of the region bounded by the graph of y equals f of x. So here, this is y, oops. So this is y equals f of x. And then the problem gives us some info about the area of the region bounded by the x-axis and f along some intervals. And ultimately, the problem is to determine, let me just go a little bit here, this integral. Let me just write that down here. Determine the integral from -5 to 2 of f of x dx. I guess there's just some typesetting problems here, but this is the problem, okay? Now let's look at what are the given info in order, because we don't know exactly how f looks like, because otherwise you can compute it using the fundamental theorem of calculus. But in the absence of the explicit form for f, let's take advantage of the info from the problem. First, we were told here that the area between f and the x-axis from -5 to -4 is 176. So from -5 to -4, the area is 176. So here, the region, or this shaded region, is above the x-axis. So that means the integral is exactly the area. So the integral from -5 to -4 of f of x dx is the actual area, right? Which is, according to the problem, is 176. Okay. In contrast, for the next interval, in the next interval, we were told that or in the next clause of the sentence, we were told that the area bounded by f and the x-axis on -4 to 1 is 1256. But where is that located? This is that region from -4 to -1. Okay. bounded by f and the x-axis, and we were told that the area is 1256. That's the area, right? But notice here that the region is situated below the x-axis. So that tells us that the integral from -4 to 1 of f is not equal to 1256. That's the area, but the area is always in absolute values. Integrals are measured as directed areas. So since the region from -4 to -4 to 1 entirely lies below the x-axis, so this integral is -1256, right? Or if you want to look at it using the concept of shaded of integrals as area, to compute the area of this region, you do top minus bottom, right? Integral from -4 to 1 of top minus bottom, but the top here is the x-axis, which is 0, minus the bottom, which is f of x. So that means -4 to 1 of negative f of x dx. This is the one that is equal to 1256. But I'm interested on the integral of f, not the integral of negative f. That's why if I multiply both sides of this equation by negative, I'll get this info. All right. So two ways to look at it. Just plainly recognize that the region is below the x-axis, or set it up using areas like this. But ultimately, you'll get the same conclusion that the integral of f is equal to negative the area 1256. And then the third info is that the area between f and the x-axis on 1, 2 is 176. So from 1 to 2, this is the area. And this is 176. Again, the region is entirely above the x-axis, so this is exactly the integral from 1 to 2 of f of x dx. All right. So going back to our problem, we want to determine the integral from -5 to 2 f of x dx, but we know the value of the integral over subintervals. So we will use the additive property of the integral, meaning I can split this up into subdivision points. So what I'll choose is to exactly write it as the integral from -5 to 4, because I know that value, plus integral from -4 to 1. We also know its value, and plus the integral from 1 to 2 of f of x dx, right? And then we plug in this the info from the problem. Well, from -5 to 4, we were told it's 176. And then from -4 to 1, we know it's -1256. And from 1 to 2, we know it's another 176. So this would be what? 352 minus 1256, if I'm not mistaken. Can you guys check my arithmetic here? I hate doing arithmetic, so yes, this is -904. Okay. Does this solution make sense? All right, I hope it does. Okay. And then let's go on. If you don't have any specific question in mind, I'll go to problem 1. Again, don't be shy. Send in your specific questions. I'll be more than happy to help you. Even if it's in the practice test, an ongoing quiz, or your written homework. It's just that I don't want to volunteer solving them for you. I want the questions to come from you guys, so just let me know. While waiting for your questions, let me do problem 1 here. Find the average value of this function over the interval 0, 4, and determine a number c in the interval where f equals the average value. Well, it's just a quick recall, so perhaps you can do this quickly. First, we need to find the average value. Remember, the formula for the average value is 1 over the length of the interval, which is b minus a. In our case, we have the interval 0 to 4. So b is 4, a0, and then integral from a to b of f of x dx. But the function f is given to be 12x minus 6x squared dx. Good. And once we evaluate this, that will give us the average value. So if we integrate, I'll have 6x squared minus 2x cubed, evaluated from 0 to 4. Okay? And then let's use the fundamental theorem of let's evaluate it. So I'll have 1/4 times, I'll plug in the upper bound, so that's 6 times 4 squared minus 2 times 4 cubed minus 0 minus 0. So luckily, this will just be this, because the lower bound when plugged in will just give us a bunch of zeros, so that's fine. And then I hate working with large numbers, so I'll use a trick here. I'll factor out the 4 squared out of the second factor, because both of them has a 4 squared. Then I'll have a 6 left on the first term, and a 2 times 4 left on the second term. And then I can cancel the 4 in the outside here by one of the squares there. So that would be a 4 times 6 minus 8. So this would be 4 times -2. So this is -8, right? Or you could have evaluated everything, 6 times 16 over here, and then 2 times 64 over here. That's fine. But I hate working with large numbers, so I try to take advantage of these algebra tricks to make the numbers smaller and much more manageable, at least for me. All right, good. That's the average value. But there's a follow-up question. We need to determine a number c in the interval where f equals the average value. So we need to find a c in the interval 0, 4, such that f of c equals the average value, which we now know to be -8. So f of c, we plug in c into the function f. So we'll have 12c minus 6c squared. That's the function f, plug in c, equals -8. And then I'll just rewrite it as 0 equals 6c squared minus 12c minus 8, right? And then I can divide both sides by 2 just to make the number smaller. So I'll have 0 equals 3c squared minus 6c minus 4. All good so far? Again, guys, I'm warning you, check my arithmetic. I might be making silly mistakes here. Okay. And then I don't know if this is factorable. I don't think it is. So I'll use the quadratic formula. So this is another helpful tool that you need to recall, because this will come in handy if you need to solve a quadratic equation such as this. So c equals 6 plus or minus square root of 36 minus 4 AC all over 2a. Okay, then I'll simplify. This would be 6 plus or minus root of 36 plus 48 over 6. So this would be 6 plus or minus root 84 over 6. And then 84 can be rewritten as 4 times 21. And then I can take 4 out of the square root. So I'll have 6 plus or minus 2 root 21 over 6. And then divide both terms by 6. I'll have 1 plus or minus root of 21 over 3. Okay. So these are the two candidates for our C values. But remember, we're only interested at C values that are between 0 and 4. Note that 1 minus root 21 over 3 is less than 0. So it won't qualify. I know it is because root of 21 over 3 is definitely greater than 1, okay, because root of 21 is greater than root of 9. But 1 plus root 21 over 3 is our desired value for C, because it's positive, and the mean value theorem guarantees that there would be a number on the interval 0 to 4 that will give us where the function will attain its maximum, its average value. It is not the negative, this is not 1 minus root 21 over 3, so it must be the other one. And true enough, if you use a calculator to verify, this is about 2.51 or 2.52, which is still inside the interval 0 to 4. Okay. Okay, so I see that there are some questions in the chat. Very good, I like that. So instead of proceeding with the rest, I'll address your questions first, because these are quite interesting. Good. I'll start with Fatuma's question. Here, R is the specify that R is the region in the first quadrant with area of 56 over 5, and its centroid is at 5/7, 7/4. Find the volume when the region is rotated about x equals 0. Okay, so unfortunately here you cannot use the disk or the washer method because you don't know exactly how the function f looks like, or what are the equations of the graphs that bound the given region. All we know that this is a region in quadrant 1, but I don't know exactly how the region looks like. So let me just draw a random region here. Suppose this is the region, okay? And the area of this region is said to be 56 over 5. That's the area. And the centroid is at 5/7, 7/4. And the centroid is a geometric center. So let's assume that is 5/7, 7/4. Of course, as usual, my figure is not drawn to scale. And we want to revolve it around x equals 0. So we revolve it around the y-axis. So we revolve it that way. For problems like this, if you know the area of the region and you know the centroid, it would be the most convenient way of solving the problem is Pappus's theorem. Right? So by Pappus's theorem, let me go a little bit lower here. We recall that the volume of a solid would be the area of the region times the distance traveled by the centroid. Okay, that's what Pappus's theorem tells us. So first, area of the region. Well, the area of the region is given from the problem. It's 56 over 5. Done. Times the distance traveled by the centroid. So let's see how far the centroid will travel here. Well, remember that the centroid is here, and the region is to be revolved around x equals 0. So the centroid will travel along a circular path as we carry on the revolution, right? So because that means the centroid will travel in the three-dimensional space, but that will follow the path of a circle, right? So Pappus's theorem required the area to be multiplied by the distance traveled by the centroid, and the centroid will travel along the circumference of the circle. And remember, the formula for the circumference of the circle is 2 pi times the radius. Okay. Can you guys tell me what is the radius of this circular path on which the centroid will travel? I guess it's easier to look at it or to determine it using a figure. Yes, that's going to be 5 over 7. That's going to be the radius, because the radius is from here until here. And that's basically the measure of the x component, right? Whenever measuring something from the y-axis towards a point on the right, that's always x units. and our x value for the centroid is 5/7. Okay, and so that would be our second multiplier here, 2 pi times 5/7. I can cancel the 5's there, and then we'll have 112 over 7 pi cubic units. That would be the area of the centroid. Sorry, the area of the solid. And this is an interesting result because all you need to do is the radius and the centroid. So if that is given in the problem, then this is the most convenient solution here. Okay, I hope that helped Fatuma. Oh yeah, you identified everything correctly. Or perhaps you just forgot the 2 pi. A common pitfall among students is that they forget the constant 2 pi for the distance traveled by the centroid. So you always remember that the centroid traveled or travels along a circular path. So you need to measure the circumference of that circular path taken by the centroid. So it's 2 pi times the radius. And it's better to have a picture side by side so that you can identify exactly what is the radius, because that changes with respect to the axis of revolution. Okay. Now let me see Christina's question. Okay. So here we will sketch the region bounded by the following curves. X plus y equals 3 and y equals 2/3. Then find the volume generated by revolving the region about the x-axis. Any particular problem here? So here you need to find the regions. So so we need to evaluate the integral. Yeah, Fatuma, that's a common problem, because usually there's a lot of formulas, or there are lots of formulas that we need to remember for this chapter. Some has 2 pi radius times height, some has a pi r squared, and so on. So it's easy to confuse and mix up these formulas for certain applications. So that's why I usually start with a figure, and then I analyze the figure, and I see, oh, the distance traveled by the centroid is actually a circular path. So I know that I need to use 2 pi r rather than pi r squared. Okay, no problem, Christina. Let's try to answer it step by step. Okay, let's sketch the region first. And again, at least for me, this is the crucial part because everything for me relies on a geometric or a visualization of the problem. It's easier to analyze everything if you have a clear picture of what's happening. So first, y equals 2 root x. So that's just a semi-parabola. When x is 0, y is 0. And then it will just go this way. Okay. And then the next one is x plus y equals 3. So I can rewrite it as y equals 3 minus x. I should have used a different color there, but anyway. Okay. So when x is 0, y is 3. And when x is 3, y is 0. That's a line. Okay. And then we have another one, y equals 2/3. So y equals 2/3 should be somewhere here. Let me use a different color here. So the region bounded by the 3 graphs would be this. All right. Now, we want to find the volume of the solid that is generated when we revolve the region about the x-axis. So the axis of revolution here is the x-axis, so we're working here. What type of strips did you use, Christina? because you have the option here. The problem didn't tell us specifically what type of strips or what method to use. So you have the option either use horizontal or vertical strips. But in choosing what type of strips, you should also take into account that here you need to evaluate those integrals. So we want to choose the easier path. I mean, to find an easier integral to evaluate to lessen the chances of us getting the wrong integrals. So here I will use if I will to choose, I will use it using horizontal strips. Because if I will use vertical strips, if my vertical strip is here, okay, that means it's gonna be red minus green, right? Top minus bottom. But if I am here, I will use top minus bottom. That's gonna be blue minus green. So I need to split the integral up into two pieces. But if I will use horizontal strips, it's always right minus left, right? The right function here is the blue, the left function is the red one all throughout the region. So there's no need to split the integral up into several pieces. So I'll choose horizontal strips here. And remember that horizontal strips always go with the variable y. And then we need to bound the y's, right? So the lower bound for the y's would be 2/3, because the region starts precisely when y is equal to 2/3. And when will it end? It will end here at the point of intersection of the red and the blue graphs. So we need to solve the intersection of the two. We know that the red graph has equation y equals 2 root x. The blue curve has equation y equals 3 minus x. So I'll just solve them. I can solve them, but well, I'm looking for y, so maybe it's easier to solve first for x in terms of y. I mean, here I can square both sides, so I get y squared equals 2x. Oh, sorry, 4x, because I'm squaring both sides. And then I can divide both sides by 4 to get x equals y squared over 4. And then here, for the blue graph, I'll have x equals 3 minus y. Okay, so now to find the point of intersection, I just need to equate these two guys together. So I need to solve the equation y squared over 4 equals 3 minus y. I'll get rid of the denominator first, so I'll multiply both sides by 4. So I get 12 minus 4y. Let me just get rid of this for a moment. Okay, and then we'll have y squared plus 4y minus 12 equals 0. Okay, and then can we factor this? I think we can. We'll have a y times, let's try 6 and 2. Then I'll have a positive here and a negative here. Is that correct? Negative 12, 6 minus 2, I guess so, right? So the points of intersection here happens at y equals negative 6 and y equals 2. But this is an extraneous root because y cannot be negative, because y is equal to 2 root x, it should always be positive. And another thing is that looking at the graph, we are expecting a positive point of intersection because the point of intersection is over here. So according to our calculations, that would be x equals 2, right? So the upper bound for my integral, which I got earlier, would be equal to 2. Okay? And then let's look at the integrand. Well, what method are we using here? I'm using horizontal strips. That's parallel to the axis of revolution. So I will use the cylindrical shells method, right? Because again, your strips are parallel to the axis of revolution. If it's perpendicular, you're going to use the disk or the washer method. But here we have the shells method. But in the cylindrical shells method, the integrand will be 2 pi radius times height. So I can put the constant 2 pi right there, okay? And then I'll determine the radius and the height of the cylinders. Again, it's easier if you have a visual or a visualization of the cylinders. So as you do the revolution, the cylinders will look like this. Okay, or something like this. I hate sketching 3D, so bear with me. But essentially, this is how the cylindrical shells will look like. So the radius will be from here until there, right? But remember our convention, whenever measuring something from the x-axis upward arbitrarily, that's always a y units, right? So that means the radius of the cylinders is equal to y, and then the height would be what? The height is nothing more but the length of the horizontal strip, right? And how do we measure the length of a horizontal strip? It's going to be right minus left. Good. So the right function here is the blue one. The blue function is 3 minus y minus the left function is the red one, which is y squared over 4. Okay. Christina, did you get the same setup?
Could I ask a question for just after you're done with this problem?
Yeah, sure. Go ahead. Mm-hmm.
After you're done, I realized when I was going through the review, I just was not that I was mixing them up, but like after I drew my like graph and like differentiated which one I had to use, like disc or washer, that like when I'm setting up the problem, I either mix something up or like I don't separate the integral.
Oh, I see. Yeah. Okay. Yeah.
So
Okay,
do you have
great,
like
Chris.
practice?
Yeah. Okay, yeah. I can do that. I guess Christina answered. Okay, now you have this, but I guess you can integrate it now because it's an easy integral. So you just carry out the multiplication by y in the integrand, take 2 pi out, and then everything would be straightforward. Okay. All right, so if that's fine, Christina, you can do the calculations here. So I leave that to you. Then I'll go back to Fatuma. Sorry, Fatuma, what's your question again?
Just when like I was doing practice questions, I knew what to differentiate, like if I was using disc or washer, but sometimes when I have to like rotate the y-axis or the x-axis, I would like mix up the equations. So like, do you have like a few practice problems that you could do just so I could see?
Okay, yeah, sure. Basically a review of setting up the integrals that will give you the volume.
Yes.
Okay, yeah, that's fine. I have here this problem number 7. I encircled it, though the functions doesn't seem very complicated. But I guess the important thing is for you guys to be proficient in applying the process, because everything will just fall into place if you know exactly what to do. I mean, it doesn't matter how complicated the functions would be, but if you know the process, then it should be okay. So yeah, will this be fine? And then we'll just play about with the axis of revolution.
Yeah. That's fine.
Yep. Because I know some students prefer to answer complicated functions, but usually if you start with very complicated functions, then you'll focus more on looking at the functions rather than understanding the concepts. But if you understand the concept, whatever function is thrown at you, then you should be able to set up the integrals. Okay, so let's play with this. Okay, so the region is x equals y squared and y equals x over 4. So again, I encourage you to always start with having a good picture of the region, or at least an idea of how the region looks like. Right? And because most of the analysis can easily be carried out if you do it visually. So the region is bounded by x equals y squared. X equals y squared is a parabola that opens to the right with vertex at y equals 0. And then when y is plus or minus 1, x will be equal to 1. Okay. So this is the graph of x equals y squared. Or in preparation for solving for y in terms of x later, I can say this is the same as y equals plus or minus root x. Okay. And then the other one is y equals x over 4. When x is 0, y is 0. Lucky us, we get one of the points of intersection there. When x is equal to 4, y is equal to 1. And so we'll have this graph. So let me just extend this a little bit. Okay, there you go. That's the second point of intersection. The blue graph is y equals x over 4, or equivalently x equals 4y. Okay. And then it's nice to know what are the points of intersection. So the points of intersection here can be obtained by putting at least one of the versions of the two equations equal to each other. So perhaps I'll solve for the x's here. So, or actually for the y's, I think that's easier. So here, x is equal to y squared. But for the second equation, x is equal to 4y. So let's put the x's equal to each other. So x equals y squared on the red, x equals 4y on the blue. So that means at the points of intersection, those x values must agree to each other. So y squared must be equal to 4y. So that means we'll have y squared minus 4y equals 0. So that means we'll have y times y minus 4 equals 0. So y equals 0, as we expected earlier, and y equals positive 4. So this point of intersection happens at negative 4. Sorry, positive 4. Okay. And what's the corresponding x value there? The corresponding x value there would be, you plug in y equals 4 into one of these equation. When y is 4, x would be 16. Okay, so this point of intersection here is 16, comma 4. All right, and the shaded region is this. Now we're ready to answer some of the problems. Let's start with problem A. Problem A tells us to set up the integral that will give the volume if the region is rotated about the x-axis. Okay. And hold on, let me just copy the figure for our next problem for the next sub-problem. Okay, here we go. So we will revolve it around the x-axis, but problem A requires us to use the disk or the washer method. Now for the disk or the washer method, the strip should be perpendicular to the AOR. Here the AOR is horizontal, so in order to use the disk or the washer, we should use vertical strips. Again, disk washer needs perpendicular strips to the AOR, okay? Now, so since we are using vertical strips, the integral will be an integral in x, right? Vertical always go with x, horizontal always goes with a y, okay? And then what are the bounds for x? Look at the x values where the region started and ended. It started at x equals 0 and ended up at x equals 16. So the bounds here will be from 0 until 16. And then are we using disk or washer? Well, to determine that, you should draw a vertical strip from the AOR towards the edge of the region. But if you do so, notice that part of this vertical strip that I drew lies outside of the shaded region. And whenever that's the case, then we should use the washer method. And the washer method requires the integrand to be pi times outer radius squared minus inner radius squared. Okay. That's for the washer method. Okay. The washer method is used if your solid has a hollow inside or a hollow interior, just in this case, because hopefully you can imagine when you do the revolution here, you'll get a sort of a bow-like figure or something like that, but the interior would be hollow because there's an empty space here. So essentially, this is empty space when you do the revolution. So that means you don't get the entire the volume is not entirely of that solid, but you need to subtract from it the volume of the hollow, right? That's why you have minus inner radius here, right? Okay, now it's outer radius squared minus inner radius squared. Where is the outer radius? The outer radius is this, the entire thing. But essentially, it's the length of a big vertical strip. So it's top minus bottom. The top function is y equals root x, right? So that means root x minus the bottom function, but the bottom function for the big radius is y equals 0. So you get root x minus 0 as your outer radius. On the other hand, the inner radius represents the radius of the hollow region, okay? So here, the inner radius would be from the AOR towards the starting boundary of your shaded region, right? But you can imagine this to be the length of this vertical strip. So it's a vertical strip again, so it's going to be top minus bottom. But the top would be the blue line. The bottom is y equals 0. So that means this would be what? X over 4 minus 0. So when you evaluate this, this would be the integral that will give you the volume. Okay? Is that good?
Yes.
Okay, and then let's try part B. For part B, we have the same shaded region, but same axis of revolution, but this time we are required to use cylindrical shells. Now, cylindrical shells require the strips to be parallel to the axis of revolution. So that means we need to use horizontal strips here. And horizontal strips always go with a variable y, okay? So here we are integrating with respect to y. So the bounds for the integral will be the starting and the ending y value for the region. Well, here the region started where? It started at y equals 0 and ended up at y equals 4. So our bounds would be 0 and 4. And then this is cylindrical shells method. So the integrand for the cylindrical shells method is 2 pi radius times height. Okay, R and H are the radius and the height of the cylinders, right? So I'll just copy the 2 pi first so that we won't forget. And then it would be easier if you can draw at least half of the cylinder. So when you do the revolution, the cylinder or half of the cylinder will look like this when you perform the revolution, right? Now, what is the radius of this cylinder? The radius of the cylinder is from here until here. That's R, right? But our convention says that whenever measuring something from the x-axis upward, that's always y units, okay? And can I use y in my integral? Yes, because luckily I'm integrating with respect to y. So y is the radius, so I'll put that here. I'll just put an arrow here to remind you that that's the radius. And then the height. What's the height of the cylindrical shells? Well, the height of the cylindrical shell will be this, right? But that is a horizontal strip. And we measure the length of a horizontal strip using the formula right minus left. So here, let's look at the right function. The right function is the blue function, which has equation x equals 4y, minus the left function is the upper parabola. So the upper parabola has equation y squared. And so that would be the volume. All good?
Yes.
Okay, now let's play a little bit, and I'll diverge from the questions there and give you this additional one. Oops. Same region. Okay, but let's say the axis of revolution is at y equals -2 instead. I don't know if you will be given problems of this sort because I don't remember in the textbook if they consider axis of revolution that are not the coordinate axis, but it won't hurt to know this. And I guess this will give us more insight on how to set up integrals for the volume, all right? So, and let's say you are not told to use any particular method. So here you have the option. Actually, for me, my go-to choice for the type of method to use would be cylindrical shells, because that will entail just an actually that will entail a simpler integrand compared to what we'll get if we're using the washer method, right? Because the washer requires pi times outer radius squared minus inner radius squared. So I'm thinking that might entail a lot of calculations before I get to the actual integration. But the cylindrical shells method has a convenient form 2 pi radius times height. But sometimes washer or disk method can be simpler, but my personal choice is to try cylindrical shells first, if that would be easy. So if I'll go along with that, so the AOR is horizontal, so I need parallel strips, so I'll use horizontal strips. And horizontal strips go with a variable y, okay? And then we know from earlier that the bounds for y are 0 and 4. Remember that the bounds are independent of the axis of revolution, because the only consideration in finding the bounds for the integral will be the starting and the ending y value of the shaded region, regardless of the axis of revolution. So still, my integral here would be an integral from 0 to 4. What can vary, though, would be the integrand, because definitely this will be like sort of a larger solid in terms of the area it covers, right? But there's an interior, so basically, yeah, this might be bigger than the previous one. Okay, though I'm not sure unless we evaluate the integrals for sure, but I imagine this should be larger. So let's see. Remember, it's 2 pi radius times height. Now the radius, again, I'll draw a cylinder or half of the cylinder. I have here fatter cylinders, right? Okay. Now, what is the radius? Can you guess what would be the radius of this cylinder? Any guess from anyone? There are no deductions for wrong guesses, so okay. Maybe you're too shy, but anyway. So remember that from the y-axis, from the x-axis upward, that's always y units, right? But that doesn't encompass the radius I'm measuring, because the radius I'm measuring is from the AOR towards the end of the cylinder. This is the radius I want to measure. But again, y is only from the x-axis upward. So that's y units. So I need to measure from what is this until here, just to complete the total radius, right? So now I guess it would be clear. What would be my radius? Would you agree it would be y plus 2? Because again, from here until here, that's y units. But from the y-axis towards the AOR, that's 2 units. Okay, so that makes the radius of the cylinder a total of y plus 2 units. Okay, and then the height of the cylinder is this. That's a horizontal strip. We all know how to measure a horizontal strip. It's right minus left. So here we'll have 4y minus left, which is y squared. So this would be the volume of this larger solid. All right, does this make sense to you? Okay, if I can borrow maybe 2 or 3 minutes, I can give you another example. Same region, but this time, let's say the axis of revolution is x equals 20. Yeah, it's usually easy to confuse these measurements. So I usually prefer to have a visual analysis because that makes everything easier. Right? So for instance, rather than memorizing some formulas, you can generate a formula for all of these with several cases on it. But I hate memorizing formulas, and actually it's useful to understand the process and the concept behind those formulas rather than just memorizing them, right? Okay, so for this problem, we have the same region. Now the AOR is at x equals 20, okay? Now I'll still use cylindrical shells. That's my favorite. But here the AOR is vertical, right? So that means I should use parallel strips. So that will require me to use vertical strips as well. But again, vertical strips go with a variable x. So I'll have dx. Then what are the bounds of x? Again, the bounds of x would be this. The bounds for x would be the starting and ending x values for the region, regardless of the axis of revolution. So that means region starts at x equals 0, ends at x equals 16. So those would precisely be my bounds here. And then it's cylindrical shells method. So it's 2 pi radius times height. So a typical cylinder will look like this. It's a very fat but short cylinder. So that's half of the cylinder. And then I'll start with the height. I guess that's easier because the height will just be how long is our vertical strip, right? That's the height of the cylinder. It's top minus bottom. So top minus bottom will give us what? Top is the parabola, so that's positive root x, minus the bottom, which is y equals x over 4. So that's the height of the cylinder. But now let's look at the radius. Where is the radius? The radius of the cylinder is here. Or perhaps let me use a more vibrant color. Yeah, there you go. So this is the radius that we need to measure, okay? But how do I measure this? Well, you can remember that whenever measuring something from the y-axis towards an arbitrary location to the right, that always gives you x units, right? That's the convention. From the y-axis towards the right, x units. From the x-axis upward, y units, okay? But I'm not measuring this because that ain't the radius of my cylinder. The radius of my cylinder is this guy, the one that I keep on tracing. So that fat line there. So any guess on how long that radius is? At least from the picture, I hope you can measure it. Any guess? Come on, guys. You don't really want to guess, but would you agree it's going to be 20 minus x? Why 20 minus x? Because it's going to be 20 minus x because here, the entire thing from the AOR towards the x-axis, that's 20 units. Good. But I am not measuring the entire thing, but I am measuring just starting from here until 20. So that means to get this length, I should subtract x from 20. So hence I get 20 minus x, right? Oh, Fatuma, you got it on the second try. It won't just be 20 minus 4. Why? Because if my cylinder is here, if my cylinder was here, definitely it's not going to be 20 minus 4 because this is not 4 units. That can be any x unit. So in general, that's going to be 20 minus x. All right. Okay, so I used 5 minutes of your time in Exas, but Any quick questions before we call it a day? Any clarificatory question?
So because we don't know like the green portion of the x, I can't do 20 minus x, right? Or 20 minus 4.
Yeah, because the region is not the value of x on the cylinders, or with respect to the cylinders, are not always equal to 4. Because if your cylinder is like the green one, which is to the left of 4, definitely it's going to be not, it won't be 20 minus 4. It would be 20 minus x. We don't know exactly what x is, but it works for any x from 0 to 16. So that's why you can remember that if you're measuring a random point from the y-axis towards the right, just say it's x units, because we don't know the exact value. The same thing, if you are measuring something from the x-axis upward and you don't know exactly what that point is, call it y units, and that should be fine.
Okay.
All right.
Thank you.
You're welcome. Yeah, good luck everybody on the test. Let's see each other again on Monday, and let me know how the exam went. All right. Bye, guys.